Hello, and welcome to the MIT Beaverworks Autonomous RACECAR course. RACECAR is an introductory robotics course for students with an interest in programming, hardware development, robotics, research, and most of all, racing race cars. During the course, students work in teams of 4 to 5 to write and optimize scripts that drive their cars through a series of increasingly complex tracks. There are two main components to the summer course. First, the students learn to program their own autonomous system using the RACECAR Neo, a race car platform built by MIT. Using the sensor stack on board, which contains a color camera, LiDAR, and inertial measurement unit, the students complete a sequence of obstacle courses that test the rigor and flexibility of their algorithms. Some examples include the Assisted Driving Challenge, line following, safety stop, wall following, and sign detection. Once students are comfortable with programming the autonomous car, they are then introduced to the research component of the course. Using the robotic platform they are provided, we ask the question, what problems in the autonomous vehicle industry can you solve with this robot? During the course, students engage in brainstorming sessions, collaborative discussions, and experimentation to develop a clear and coherent solution to their problem statements. Advised by experienced instructors and professionals from MIT and Draper, students assemble a research paper and presentation to present their findings to the BWSI community. During the final week of the course, students integrate everything that they have learned into programming the cars for the final challenge, which is the Grand Prix. This is a custom-designed, multiple obstacle racetrack located at the MIT Johnson Ice Rink, in which students showcase their capabilities of their autonomous robots once and for all. From all the instructors and teaching assistants, thank you for your time in watching this video, and we welcome you to the Beaverworks Autonomous Racecar course. All right, and welcome to the Autonomous Racecar Research Proposal Seminar session. I am your host, Chris Sly, the lead instructor and the course developer for the Beaverworks Autonomous Racecar program. Today, I'll be monitoring the presentations as well as managing the questions and answers session. We have 9 incredible presentations to share with you today, with topics ranging from detecting imperfections in autonomous vehicle behavior to improving the safety of driving and applying innovative algorithms to make autonomous vehicles safer for all. This year, students were challenged to identify several problems in the autonomous vehicle industry that they could research and innovate upon using their 1/14th scale autonomous race car. The overall goal here is to answer the big question of, if autonomous vehicles are as safe as everyone says they are, why don't we already use them in our everyday lives? In this session, students will present research proposals, which is a blanket summary of the problem they are currently researching and what results could be possible given more time, money, and resources. As we certainly do not have infinite time here in our short 1-month course, we hope that this opportunity can bring potential to any ideas or projects that our students would like to take on in the future. That being said, these students have already achieved so much in such a short span of time. We hope you find their presentations insightful and educational, and we encourage you to ask questions in the Slido. Students will receive 5 minutes per presentation and 5 minutes to then answer any questions. Thank you for watching and enjoy the show.
Hi, I'm Kripa.
I'm Serena.
Hi, I'm Stiti.
And I'm Zoe.
So our research is on comparing the accuracy and efficiency of machine learning models and a claw algorithm in low lighting in improving low lighting images in classification in AVs. So what is the problem right now? So currently autonomous vehicles cannot achieve the same amount of perception and performance they do in the day due to how they are trained and the data sets that they use. So they have, and this causes the car to not be able to properly detect objects and road marking recognition, and this compromises on the safety of the driver as well as the pedestrians around them.
So in current automation, autonomous vehicles often use machine learning models to detect and classify objects such as road signs or pedestrians. And these are based on training data sets as for what they should detect. Based on this, one would think that the training data sets are very diversified to include images at night and to include images from low lighting. But the issue with this is that the images are still very low quality. They have very poor resolution, which can lead the car to misidentify or completely miss the object in the image, which can cause erratic and possibly dangerous behavior at night, as can be seen by the statistics. So nearly 1.5 million crashes occur at night. Almost half of the fatal crashes occur in the dark, even though only 25% of driving happens at night. And from all autonomous vehicle incidents, there's only been 946 in 2024, which really shows us the weight of how important it is to solve the problem of driving at night and detection.
So our proposed solution is to use CLAW, which is contrast-limited adaptive histogram equalization, an existing algorithm to enhance contrast, and machine learning model to process low light and low contrast images separately.
So what exactly is CLAW? CLAW is a method of histogram equalization in which images are separated into several sections, and each section's contrast is equalized with histogram equalization. This forms an overall clarified image that avoids flatness and looks realistic, as you can see in the image shown in the slideshow. So first, we will set up our experimental and control group design. For our experimental groups, we will use a machine learning modified image dataset and a CLAW modified dataset, while our control group will use raw unmodified images.
And our data collection is obviously to take photos of signs in varying environments such as dark, and then those unprocessed will be our raw data set, which is going to be our control group, and those are processed will be the experimental group.
So our two experimental groups, as I mentioned before, so the first experimental group involves a machine learning model, and that will be trained to enhance contrast in images. Our second experimental group will involve passing the image dataset through CLAW, and in both experimental groups, the produced datasets will be fed into an object detection model, and the performance will be compared.
Our test will be combined with the successful matrix, which will measure the accuracy of both experimental groups, compare them, and also measure the efficiency of each model to see which one is in real time. So this is our success metrics. We will evaluate the object detection accuracy for both CLAW and our machine learning model to see which model processed the image better. And then we'll also measure the processing time since autonomous vehicles reacting in real life in real time is very important.
Thank you. Any questions?
All right. Thank you to Team 1 for your excellent presentation. I will now be reading the questions from the Slido. First question. If you continue with this research, what do you anticipate would be the timeline of this experiment?
I can take this one. So for taking for collecting our data set, we'll have a training and a testing data set. So the training data set we will likely be using existing images and existing databases to source those. So that shouldn't take much time in terms of data collection. For testing our testing data set, that will maybe involve 2 to 3 days of data collection to ensure that we have a robust data set that we can test our model on afterwards. The main part of this project that would take the longest would be the training the model, which can vary depending on how difficult it will be to train that model, but I would estimate about 3 months minimum to properly tune that out, and then more realistically 6 months to really iron out any issues or issues in how it's responding.
Thank you. Next question. What would be the anticipated cost of this project, and should it be executed in full?
We currently don't add any other sensors other than like the RACECAR Neo, which costs like $1,000, and a camera to take pictures for data collection. The claw algorithm should be able to run on this RACECAR Neo, but we haven't start the experimentation process yet. So we don't know if all of those, like the claw and the machine learning model, will be able to implement in real life. Also, this research is to evaluate which one is better.
Can I also add that as of right now, we don't believe that there will be any additional costs, as Zoe said, other than the race car Neo. And that may change in the future depending on what roadblocks we encounter.
All right, final question. How could different street lights and other cars on the road affect your data sets? Is this something you have considered?
So I guess we also want to like diversify our data set as much as possible. So we want to include like streetlights with like some lighting and like extremely dark images in places with like no lights at all. But we also want to consider like sets where there's like cars coming head on at you or cars coming from behind you. So we will include like all of those in our data sets for training as well.
All right, thank you once again, Team 1, for your excellent presentation. We will now move on to Team 2.
Hi, I'm Dinesh.
I'm Rashik.
And I'm Angela. Our fourth team member, Annabeth, cannot unfortunately be here right now, but you will hear from her later.
And I want to get started by asking you, imagine you're driving on the road and suddenly it's a sunset and you're passing through a group of trees and the shadows and light keeps rapidly flickering and you can't see anything. But imagine how it feels to be the autonomous car in this scenario. Next slide.
This into our problem statement of how autonomous vehicles can be confused by rapid changes in shadows and light that are caused by the environment, as mentioned before, trees, buildings, overpasses, etc. And this can cause them to misinterpret road markings and objects, causing issues like phantom braking and other unpredictable situations that can be very dangerous on the road.
Next slide.
According to Peter Lin, who is the director of Ethics and Emerging Science Group at California Polytechnic State University, computer vision has a very long way to go, especially with distinguishing shadows and identifying smaller objects. This can cause a phenomenon known as phantom braking, and there are many examples which are seen on the next slide of phantom braking occurring in Teslas. Phantom braking occurs when the car randomly hits the brakes, despite the fact that there is no that there are no obstacles in the way. It comes from the brake's automated safety system, and this can be extremely dangerous. On the next slide, some statistics. There have been the NHTSA has received 354 official complaints about phantom braking caused by detection and error, and and this has been covered over a very wide range of vehicles. Phantom braking can cause fatalities and deaths. There have been examples of rear-ending due to cars phantom braking on the highway and causing collisions.
Next slide. And some potential solutions that we came up with were both shadows using machine learning, where we detect the contours of the shadows and replace them with normal lighting, which is done by taking quite a bit of data by taking pictures in both shadowy conditions and regular lighting. And our other solution is to take localize points from sections of the image, and we take grayscale portion, convert them to grayscale, and we detect rapid changes in brightness. And between these frames, there'll be differences in brightness, and we take the averages of the area of light and the area of shadow, and therefore change the HSV values of the shadowed areas accordingly, so that detection algorithms in vision-based systems can run appropriately.
For our
Next
experimental
slide.
plan, first we will set up the image collection stage. This is where we will get images both for training the model and for later verifying the accuracy of it. To get the images, they'll be made with a flashlight placed behind a cardboard or foam board in order to simulate the sun behind trees, so that there's areas of both light and shadow in every image, and those will be taken using the RACECAR. In the stage, also, we will take ground truth pictures where there are no shadow in order to compare them later. Then we will execute our chosen solution to detect shadows, as Roshik just discussed, and then we will correct the shadows by referencing portions of light and adjusting HSV values so that they are more consistent across shadow and light areas. Then we will compare, to verify how well this process worked, we will compare process shadow images to non-shadowed pictures and see how similar they are, to see how, if they are more accurate to full light pictures compared to the original shadow pictures. Then we can run a series of detection tests to determine how effective it is. And the successfulness of the algorithm will be determined by if a line follower is more successful even with areas of shadow compared to unprocessed images completely.
Yeah. And this concludes our presentation. Are there any questions?
All right. Thank you, Team 2, for your wonderful presentation. Here are some questions. First question, how would you solve potential issues from falsely flagged shadows, for example, bright traffic lights on their black housings?
I think that this can be solved by using a very large training data set. If we were to go with the machine learning route, we would have to collect a very significant number of images to demonstrate to the machine learning model that not every dark object is a shadow, and that shadow, and just what a general shadow looks like. So we would need to be able to collect a very, very large amount of data in order to ensure that the accuracy of our model is as high as possible.
Yep, and with the localization option, we will detecting changes in brightness. So just regular shadows will not likely be falsely flagged, as it's actively looking for rapid changes in brightness only.
All right, thank you. Next question. How would you be able to determine if the shadows have been sufficiently removed from the image?
So that comes down to our the validation procedure in the data itself, where we will be testing, at least for the experimental design, we'll be testing it on line following, where if it can follow the line better than what the unfiltered image is, and we'd compare that by looking at contour area, or using the machine learning model, we'll use confidence level. Does the confidence change from when there is shadows to our filtered image? Does it get greater? Does it get lower?
All right, thank you. And final question. What sensors are you hoping to have in a car to aid you with this? And do these sensors exist in modern cars?
I mean, I can talk about, well, our idea is mainly to use the camera, mainly vision-based systems, as seen in like Tesla autopilots, where they rely mainly on vision and camera. And we're ideally going to use those to take the image, filter it, and then run whatever algorithm is running on the filtered image itself.
All right. Thank you once again to Team 2 for your excellent presentation. We will now move on to Team 3.
Hello, I'm Graham.
I'm Alec McFadden.
I'm Pablo.
I'm
I'm
Jaden.
And this is our presentation about autonomous vehicles at intersections and blind spots.
Each year, over 840,000 accidents are caused by a lack of sight for an obstacle, usually around something like a blind corner. So autonomous vehicles can partially fix this because they remove humans from the equation, but they can still not react to something they cannot see, such as around a blind corner.
And even though autonomous vehicles can predict that there may be a dangerous part of the road or that there may be a dangerous obstacle incoming, they may not be able to react fast enough for them to make a viable solution.
And so originally we considered equipping each car with its own sharing system for data, but we quickly realized that this would be very unrealistic and difficult to implement due to just the large amount of communications between every single car, the large amount of sensor noise, and the major loss in quality of the data that would come from this. The challenge would also be with the network infrastructure. To make car-to-car sharing work, you'd have to have so many different connections and keep establishing them and processing so much data that it would be very slow and inefficient. So instead, we pivoted to a static sensor that would be placed within the environment that we wanted, that would have a single data stream that could be accessed by multiple vehicles, which would reduce the complexity and avoid overlapping router connections and multiple different negatives that came with our first idea.
So an upscaled version of this infrastructure would be placed at high-risk intersections, such as those containing blocked lines of sight or blind turns. There would be a wide FOV camera that would have a good view of the entire intersection from above. This camera would be hooked up to some kind of computing unit that would have a TPU accelerator to be able to run autonomous vehicle detection models, which would not only tell the computer how many cars there are in the intersection, but also where they are relative to each other. This information is key to the combination of LiDAR maps. Each car would send its LiDAR data to the computing unit, which would filter and combine each of them into a global map of the intersection, which would then be sent out to each of the cars. This gives each car a better understanding of the intersection and what may be going on around the corner. This also lowers the computational load on each car.
So in order to test this concept with our race cars, we would create a sort of mock intersection in which we had a sensor placed at the middle of two cardboard lanes, and we would have a piece of debris, which would also be cardboard likely, between the two cars. We would then run the cars at each other toward the intersection, both testing what happens with and without the sensor, communicating between the two cars. And that would allow us to determine whether or not our system works. This would be able to simulate debris in an actual road. Eventually, we would scale this up to actual full-size cars.
Thank you. Are there any questions?
All right, thank you, Team 3, for that great presentation. There are some questions in the queue, so I will ask the first one. What were some other sensors that you may have considered that did not make the cut for your experimental plan, and why not?
So for us, one of the sensors that we were considering was a LiDAR. Within the budget range that we were thinking about working through, we would have to use a 2D LiDAR, which to place within an intersection to collect a reasonable amount of data that would help us, it would have to be placed within the intersection on the floor or somewhere near to the floor. And we realized that having a object within the center of the intersection would kind of destroy the entire point of this arrangement of sensors. So we decided that it wouldn't really make the cut. We also looked at some other sensors like a depth camera or something similar, but we decided against it as it would be a much larger computational load when you could find distance through different mathematics within the cameras.
All right, thank you. Next question. Do you anticipate latency to be an issue? And if so, how would you deal with it?
We do not anticipate latency to be an issue. So on our race car Neos, everything was running on a Raspberry Pi and a Coro TPU accelerator, and it could identify things within like less than like a tenth of a second. And also that connections between like a car and the sensor in the middle, they have very low latency as a university in Turkey has established that even with something completely blocking they cannot transmit through easily, they can still transfer up to 50 meters with less than 1 millisecond of latency.
Yeah, and also part of the point of the downscaled experiment, doing this on the race car Neos, is to see how this vehicle to infrastructure experiment will work on very low computational power cars with less than optimal sensors. And there may be some latency, but if it is very little latency, then we can be sure that when it's upscaled to real autonomous cars with better computing units, that there will be even less latency.
All right, thank you. Next question, and the final question. How would your sensor communicate with incoming cars?
So when we have um, more autonomous cars on the road than we do today, eventually most of the cars will be hopefully equipped with sensors that can receive this data from the sensors. In a current standpoint, modern vehicles would likely not be able to have these sensors, which is why ideally this would work when more autonomous cars are on the road than human drivers.
And we'd likely use some kind of protocol like Wi-Fi or Bluetooth, whichever one we find in our scaled down experiment to be the one with lowest latency. Currently, the race car Neos use Wi-Fi to communicate with computers and controllers and things like that. So we will look into those.
All right, thank you once again to Team 3. And now we will be moving on to Team 4.
Hi, I'm Prasid.
I'm Matthew.
And I'm Karen.
Unfortunately, one of our teammates is out today, so we will be covering for her. Our project is autonomous vehicles and emergency lights. As humans, flashing red and blue lights trigger an immediate reaction. We recognize danger, we slow down, but to an autonomous vehicle, those lights can mean nothing.
That disconnect between human perception and machine vision is the focus of our research. Specifically, we're addressing how flashing emergency lights can confuse rolling shutter cameras, which most autonomous vehicles use today. These cameras capture images line by line, so when exposed to fast strobe lights, they produce distorted or even unreadable frames. As a result, the car can miss other vehicles, lose lane markings, or even completely fail to perceive objects, especially at night. Now, you could ask why we cannot use LiDAR. However, autonomous vehicles use both the camera and the LiDAR together to create the most clear image possible. So a failing camera can lead to certain objects, such as lane markers or road signs being missed.
Possible solutions include implementing a global shutter that checks the entire frame altogether, which disregards rolling artifacts altogether. However, this solution requires high costs, which is something we don't currently have. So our solution is more cost effective. Our system starts with a convolutional neural network that checks each frame in real time, and if the frame is clean, it's used, and if the frame is distorted, it's flagged as bad. From there, we don't rely on external sensors, rather we reconstruct. Our system uses the last clean frame and interpolates what the missing frame should look like.
Test this on the race car by placing flashing lights along its path. By analyzing motion between previous frames, we can estimate how the scene has shifted and generate a synthetic frame to take place of the corrected one.
It's like giving the camera a memory. Even if one moment is lost to a flicker, the system can still see by predicting what would have been there. So in short, we're not solving the problem of driving through flashing lights. We're solving the problem of being able to see through them. By detecting and reconstructing corrupted frames in real time, we bring resilience to machine vision. Thank you.
All right, thank you to Team 4. Are there any questions from the Slido? Okay, here's a question. What algorithms or tools will be used for the predictive reconstruction?
I think I can take this one. So, in our solution, we did mention we would use a convolutional neural network in order to reconstruct frames, or no, we'll classify them as good and bad. And then we were thinking of creating another model, which would then use previous frames that were classified as good, and use them to interpolate the next pixel or frames that were distorted by the flashing lights.
All right. Next question. How will you measure the effectiveness or practicalness of your method compared to previous methods?
We'll probably use a control. So like we won't run any method and we'll apply our method, which is the convolutional neural network, and evaluate how much better the performance is compared to the control.
All right, thank you. Next question. What are the points of failure you can foresee?
Some points of failure we could foresee is that there are some situations where there will be many distorted frames, so relying on the past clean frame could be a lot of frames ago, which makes our system less reliable when detecting these flashing lights, which is something we will definitely try to tackle more in the future.
All right, thank you. And that is all the questions for Team 4. Now moving on to Team 5's presentation.
Hi, I'm Aiden.
Krista?
I'm Tianxi, and our teammate Claire is not here today, so we'll be covering her problem. And our problem proposal is detection of failure lanes to mitigate autonomous vehicle risks. Next slide. All right, so imagine this. You're driving down a highway and you see some faded lines. You'd be able to detect that really well, right? But it's still pretty annoying. Now imagine your autonomous vehicle that uses some sort of image processing to determine where these lines are. Would you trust that car with your life? I wouldn't. And in fact, in many circumstances, these cars have been unable to detect these faded lines and end up swerving onto oncoming traffic, risking the lives of the drivers, the passengers, and just people in general. In fact, in a study, when lane markings were 50% faded, we could detect it around 95% of the time. But as soon as it dropped down around 75% faded, accuracy went down to about 54. So that's 46% of the time where it just wouldn't detect the lane and it could swerve onto traffic. Next slide. Yeah. This is an example. It's like a 30-second example, so like just check it. It's basically this car is going through a highway, and it's basically going to swerve onto oncoming traffic. As you can see right there, it's going right now, and it has to the driver has to emergency brake stop the car. Yeah, it paused. You can move on now, I think.
Okay. So how have previous studies tried to solve this problem? So, and what were their pros and cons? So AlexNet was the first CNN-based model for detecting lanes, but it worked poorly with low contrast and texture. The puff transform didn't use a CNN, but its over-reliance on parameter tuning made it unusable in new lightings and environments. For example, when floodlights were on. ConlayNet was a more recent CNN, but it's faced a lot of difficulty with curved lanes, and over-reliance on prior knowledge has led to quick but suboptimal accuracy. Then our CNN relied on explicit features, and it couldn't detect well on different illuminations.
Next slide.
So as Chris has previously mentioned, after reviewing all the literature, we realized the drawback from each model, and our current plan is to come up with a new architecture design with a CNN transformer-based model for this specific task. So first of all, CNN is a robust machine learning algorithm that's like meant for designed specifically for image detection and information segmentation. And then it's the transformer, which is the building block of like generative AI like ChatGPT, which extracts the past information from the previous sentence, or in this case, can be the previous frames of the image, and used it to predict the future frames. So combine these two, we'll be able to aggregate spatial, which is the image itself, and the temporal, which is the over the time how does the lane change. All these queue together and combine them for the future prediction. And also, in order to increase the robustness of the prediction algorithm, we plan to use sensor fusion, which will be taking the IMU data and also the color camera, and then combining them together to work them into a ground plane, which is easier for the model to detect and run the algorithm on. And yeah, just to reiterate, this is a rudimentary design model, but it uses the transformer, which is an attention system that can aggregate data from the past and combine them with a CNN-based model for image detection.
Excellent. All right.
So Claire's not here today. We'll be covering her part. So in terms of the experiment design, first to test our model will be, so the autonomous vehicle will be the race car, which will have a IMU sensor and also the color camera. But if we don't have the race car, any vehicle of equivalent will be acceptable. And then we'll also be using tapes, which will be white and yellow to mimic the real traffic scenario, and then also need sandpaper to mimic the wearing. So in real life condition, there will be traffic erosion, rain, sun, and also accumulation of dirt and snow. So in order to mimic this, we first replacing that with both white and yellow tape, and use sandpaper to send them down and to mimic the wearing condition. And later on, we'll be running our proposed transformer CNN combined model onto this, and ideally it should be able to interpolate and predict the current faded lines, and also ideally help us to predict where the line will go out of the frame. And later, in terms of training data we'll be comparing the prediction with the ground truth data and help us improve the model.
All right.
Next slide.
Next slide. Yeah. All right. So the way we'll analyze this is we'll compare our results to first AlexNet due to its age, and our CNN, which is one of the more modern ones. It'll provide like a basic how well are we along in the spectrum. And a lot of times these models really struggle due to constrained data sets. They struggle with edge cases due to faded, like even if it's like curved lines, forks, stuff like that, it won't work well. So what we're going to do is we're going to have a basically higher data set. And we're going to compare our model to these models in terms of robustness. And this is measured in terms such as precision, recall, and F1 scores. We can also check it based on efficiency, which is the energy used, and the accuracy, which is basically just how well it detects, which is the raw percentage. Yeah, that is basically it. Yeah, any questions?
All right, so Chris has to step out for a second, so I will ask the questions for him. First question is, how do you foresee the differences between your tape and real life lanes impacting vehicles running your proposed CNN?
I can answer. So basically, what the tape is used for is just to like simulate road conditions. And the most common colors of tape for, I guess, the roads are white and yellow, which we will use. So all we have to do is basically move it onto real life roads due to we just have to make a new data set with real life roads to basically just show how well it works. This is more of like a comparison to see how it would work based on the simulation.
All right, and the second question is, what is a CNN?
So CNN stands for convolutional neural network, which is basically a sliding. So imagine the image and a sliding window of array that goes over the entire image and it aggregates information. So for each layer, you can think of it as that it extracts the most important or the most wanted feature, and as you're going down the neural network, it aggregates them, and this really enhances the robustness of the model to predict for image detection.
All right. Next question is, what would be the biggest challenge for your progress in this?
Designing the new architecture will take some time and training the model, but I do believe that it can be done and it's feasible.
And yeah, since there's a new architecture we're proposing, we're not sure about the final result. It can be positive or negative, it can be worse than RCNN. However, we expect this model to be in terms of the design architecture, it's fundamentally different from the previous network. So even if this doesn't turn out as well as we expected, it can show some difference and new ideas of this type of model.
All right. And last question is, why do you think your model architecture will work better than previous ones?
So if we look at other architectures such as RCNN, it's the way it works is basically it just cuts up the image into separate boxes, and that makes it kind of blocky and also kind of choppy. What we want to do is we want to first be able to create an actual way that it actually follows the lane instead of having blocks. And also what we do is we use past images. We use a transformer. We take into consideration past images and use it to inference and basically determine where the new lanes should be. And we could use weights to basically have it more advantaged towards the inferenced images.
Yeah, so like we mentioned, it's similar to your aggregation algorithm that it takes account into the previous frames. So instead of making a prediction solely on the current image, the model will be also looking into the past images, and this enhances robustness and avoids some random guesses or hallucination on the current image frame. Yeah, thank you.
Thank you.
All right. Thank you to Team 5 for your Q&A sessions, and thank you to Alan for covering for me. Now we'll move on to Team 6.
Hi, I'm Adi.
Hi, I'm Mahir.
Hi, I'm Guillaume.
And our research project is on autonomous driving without visible lane markers. Next slide.
So autonomous cars are trained to follow the rules of the road. But what happens if part of the road forgets to show up? Autonomous vehicles are not able to correctly position themselves when lane markers are faded or non-existent. And that's what our research is attempting to solve.
This issue is pretty significant because studies have shown that 65% of the US roads are either faded or missing for the lane markers, thus making it hard for the AVs to track and navigate through the path. Moreover, 3 out of 4 deadly lane-changing crashes happening in the world are due to AVs not being able to detect and taking incorrect decisions.
Yeah, so a lot of research has been done to explore this problem, and some of these statistics evaluate systems both in the US and internationally, such as lane departure warning systems and lane assistance systems. And as shown, when lane markers are faded by about 50%, their accuracy is still relatively high. But when that drops to 25% visible lanes, this accuracy goes down to only about half the time. And these stats and research show just how dangerous this situation can be and how big this problem can be for AVs. So our solution would be to implement a camera-based edge detection system or algorithm, like the Sobel filter or the Huff transform, and combine that with other sensors like LiDAR validation, or use map matching techniques with pre-made maps. And this solution would help estimate road boundaries and guide the vehicle even without lane markers so that it could navigate in these situations more efficiently.
Now to test for a solution, we will carry out a week-long experiment where on day one we will be setting up the tracks for both clear and faded markers to calibrate the camera, the lidar, and other sensors we are utilizing so that we can ensure they're working fine. On day two, we'll be running trials for the tracks that have clear lane markers. Chris, slide two. And we will be using and collecting, using all the sensors we have and collecting data from them and getting the LLCR data, which is basically the lane line contrast ratio, which is essentially the difference between the brightness on the lane markers and the area that's around it on the path.
Next slide. So over the third and fourth days, we'll be performing essentially the exact same trials that we performed on day two, but now with more faded lines. So we would use materials to artificially create a lower lane line contrast ratio that would be reflective of real world situations, and even go as far as to have no lane lines at all, which also exists. And we would perform those exact same trials that Adi just described. And our goal with this is to be able to compare the performance of the car in like more ideal conditions to now with more realistic conditions and see if our solutions that we're trying to implement actually have a tangible amount of success. Next slide. And then on the last day, we would be finishing up any trials that needed to be done, collecting all of our data, analyzing them, and working on your final report with graphs and just putting all the data together.
Next slide. So this is our bill of materials. These are the resources that we would need along with our RACECAR Neo. So we would use white vinyl tape and gray painter's tape to simulate both fresh new lane lines with the white and also lower contrast lines with the gray tape. And then we would also use sandpaper to artificially scuff these lane lines to simulate fading. And then finally, we would need a luminance meter, or also known as a lux meter, to measure the brightness and lux of both lane lines and the pavement around it in order for us to determine our lane line contrast ratio, which we have explained is how our measurement for how faded a lane line can be. And that would be our total cost. Next slide. And that's it. Thank you.
All right, thank you once again, Team 6, for your presentation. Now here are the questions. First question, how do you determine whether a lane is visible or not? For example, how do you say that a lane is 50% visible?
I can take that question. So, as I mentioned before, we will be using LLCR, which is the lane line contrast ratio, testing for the difference between the brightness between the lane marker and the path around it. So, the common threshold for the LLCR is 5:1. And so when we'll be setting up the experiment running trials, we'll be testing our data with this ratio and see how accurate it is with different types of lane markers, whether it be faded, clear, partially faded, or missing.
All right. Thank you. Next question. Can these methods handle all the various lanes we see on the road, like a solid white line, dotted yellow line, etc.?
Yeah, so I'll take this. Our solution still continues to involve camera. But these filters that we would use, like the Sobel filter, essentially it's an edge detector which tracks the gradient or the changing in contrast over like grayscale images. So this doesn't necessarily track like colors or the type of line, but it's more looking for edges to know where the road ends, or maybe where the car needs to stay in the path. So theoretically, it would help as long as there's some form of edge besides a lane, then our car would be able to navigate in the lane.
And to add on to that, with the LLCR, the lane line contrast ratio, it's more, well, it's why we have the lux meter. It's more about the brightness of the two like contrasting parts, the lane line and then the road behind it. So like Mihir said, with the grayscale images, it's not necessarily about the color of the line or its shape, just that contrast between those two parts.
All right. And final question. How could this be used for real AVs or autonomous vehicles?
So it can be used for real AVs. Like basically, the systems that are already running in the AVs can still be like will still remain in use, but this system that we propose can be like a fallback system that can act when there are faded line markers or partially faded or completely missing, combined with the edge detection with LiDAR validation and the camera data we will be collecting.
Okay, thank you once again to Team 6 for your amazing presentation. Now we will move on to Team 7.
Hi there, I'm Ian.
Hi, I'm Hriday.
And I'm Kieran, and unfortunately, Caitlin couldn't make it to today's presentation.
So imagine this. You're in New York City, you're driving down Broadway, heading towards West 77th Street, and suddenly, out of nowhere, a bike just shows up in the middle of the road. He's run a red light, and I mean, bikers are just like that sometimes in these big cities, and before you know it, we attempt to use autonomous vehicles to help mitigate this risk.
From NHTSA data, around 36% of autonomous car crashes are around intersections. This is due to the fact that autonomous vehicles face safety challenges in urban environments due to occlusions like buildings that block their sensors' view of VRUs. These visibility limitations contribute to collisions and remain a major barrier to the safe deployment of self-driving technology.
So in our example, we have like a car approaching an intersection, and there's a building which acts as an occlusion for a bicycle that's on the other side that's heading towards the intersection. And we want to help the car help see the bicycle, which is like a vulnerable road user or a VRU.
In order to solve this, we plan to use an FMCW radar, or a frequency modulated continuous wave radar, which is a type of Doppler radar. These radars transmit radio waves that hit objects and bounce back to the car at varying frequencies. Doppler radars provide locations of the objects in addition to direction and speed given by the frequencies. The data can then be used to predict the trajectory of the object, which can be then compared to the car's trajectory to determine whether or not there will be a collision. Then the AV will make a decision on whether or not to stop or to avoid the VRU and how to avoid the obstacle while it's still in the car trajectory. Next slide. To be more specific about what exactly we're contributing to this field, radars in regular cars can detect the presence of an object and its location, which is used for slowing down, parking, or emergency stopping. Research exists on Doppler radars in AVs to detect objects in occluded areas, and although pathfinding algorithms to avoid obstacles exist, none directly apply to radar detection, object detection. So our plan is to implement Doppler radars to plan the trajectory of the VRU and integrate that into our path planning algorithm. We will then analyze the performance of several different algorithms to determine which work best in certain scenarios.
There's a list of pathfinding algorithms that we compiled, and you might have heard of some of these before, like model predictive control and deep reinforcement learning. And the main point is that we want to test them using these metrics, and some obvious ones might be like success rate and time to collision margin, which is just the time to the collision and how it avoids it, and the minimum clearance of the car and the VRU when it avoids the obstacle. And something else we want to test is adaptation to new obstacles, is how the car reacts when we add more and more occluded obstacles and occluded moving obstacles to the.
So our experimental timeline, we plan on testing using the Doppler radar and the algorithms mentioned in the previous slide in the race car simulator. So we'll start by setting up in the simulator, adding to the simulator car a Doppler radar. Then we'll implement some different intersection scenarios, like example intersections with bikers going by at varying speeds, and various different other VRUs there. And then on these like different intersection scenarios, we'll test our algorithms based on the Doppler radar data. Then we'll analyze the data we collect from testing our algorithms in these intersections, and based on that, we'll make conclusions. Any questions?
All right. Thank you, Team 7. Now we are going to move on to the questions. First question. How is your solution different from manual cars that already have radar for detecting other objects on the road?
So I can answer this. So our solution is different from manual cars already using radar to detect objects, as it uses a type of Doppler radar which can find the velocity of the incoming objects and can also look around the corners in occluded areas. And also our solution is another degree to this is that we're using pathfinding algorithms to avoid the occluded object from colliding with us.
All right, thank you. Next question. Which car manufacturer do you believe would benefit the most from this?
Honestly, any manufacturer making autonomous vehicles could integrate our proposed solution into their vehicles. So, yeah.
Okay, and final question. How much compute power do you need to run your experiment?
Our experiment wouldn't require as much computing power as like using other things. Like, for example, if our pathfinding algorithm could use a lot of computing power, but getting the data from the radar wouldn't getting the data from the radar and processing it wouldn't take as much computing power as many other solutions.
All right, thank you once again, Team 7. Now, moving on to our final team presentation, Team 8.
Hello, my name is Connor McGovern.
Matt.
I'm sitting.
And I'm Jeremiah, and this is our project proposal on differentiating between weather impacted and noisy LiDAR data in dynamic AV LPR.
So imagine a blind person walking using a stick. They tap all the objects and obstacles around them to give them a sense of their environment. Similar to this, AVs use LiDAR as their stick, so to speak. But how does the person know what they are feeling? Well, the stick and the LiDAR can only tell if they are sensing something, not what it is.
LiDAR is an extremely useful sensor, but it's also very vulnerable to adverse weather. Snow, rain, hail, fog, and other elements can significantly degrade the sensor's performance because the data can be added with noise. Just like the analogy with a blind person, our problem is that in autonomous vehicles, LiDAR cannot distinguish or classify between weather-related disturbances and day-to-day objects in dynamic scenarios.
So some existing research has already been conducted to classify weather. However, this research has been only conducted in static scenarios where the LiDAR is not moving and the weather is not moving as well. Also, many existing algorithms exist to denoise weather-impacted LiDAR data, such as RACECAR, which is LiDAR-based place recognition, and LDR, which is LiDAR data restoration. But as you can see in the diagram, the denoising algorithms need a very specific corruption type in the data in order to denoise the actual data. So our solution is to to classify and quantify the noise introduced by snow, which can be utilized in denoising algorithms to make LiDAR data more reliable.
To test our model, we plan to use the given 2D LiDAR with different snow setups in addition to the RACECAR sim graciously provided by BWSI. The setups for this testing will include static and dynamic, which are moving situations, as well as natural, artificial, and simulated snow. Specifically, we will be using the RACECAR sim to simulate different types of internal sensor noise, such as Gaussian noise, Laplacian noise, and impulse noise. We will also be utilizing a 2D and 3D LiDAR, specifically the Unitree L2, to test our model. Next slide. To be able to test year-round, we plan to use two different setups. In the summer months, we will build a wind tunnel and blow artificial snow, specifically sodium polyacrylate, through it to simulate snowfall. While in the winter months, we will bring the car outside for extended periods of time in snowy conditions to further test our model. We will use to test the accuracy of our classification model, we will place different reference objects around the car, including walls, in order to better tune the model. Given the importance of 3D LiDARs to the navigation and localization of autonomous vehicles, recognizing the type of noise as environmental interference versus solely internal to the sensor is of utmost importance to the proliferation of AVs as safe alternative to human drivers. Next slide, please. Here's the bill of materials, and we'll open the floor to questions now. Thank you.
All right, thank you, teammate. And now we will open the floor to questions. First question, what kind of LiDAR do you need to be successful for your experiments?
I can take this one. So on the RaceCar Neo, it's just a 2D LiDAR, and we can be successful using only a 2D LiDAR. But the reason why we also plan to use a 3D LiDAR is because 2D LiDAR isn't really used at all on, well, sort of like full-scale autonomous vehicles that aren't the RaceCar Neo. So the algorithm will work for 2D or 3D LiDAR, but 3D LiDAR is more applicable to the real world.
All right, thank you. And next question. How do you protect your car from braking while doing these tests?
Oh, I can take this one. So in terms of just using the 2D LiDAR, we can use put something on the top of the LiDAR, which would still allow the LiDAR to use its full functionality to get a point cloud from what it's seeing. But with the 3D LiDAR, we'll have to experiment with different materials such as glass, such that the LiDAR can still function without being interfered by its covering. However, if we're taking it to the taking it outside to use real snow, we would definitely have to consider covering it up with something that would still allow it to function, but also protect it.
All right, thank you. And that is all the questions for Team 8. All right. Thank you to all 8 teams for presenting. We are actually now going to move on to a very special presentation by our very special research student. This year for Beaverworks, we had the great opportunity to invite some of our previous alumni students back to complete an entire research project from start to finish, from proposing a problem to analyzing it to building a prototype and iterating through it to find the best means of a solution for that problem. These research students spent an entire month doing this type of prototyping and testing, and our very own research student, Raheel, will now provide his presentation on the work that he performed this month.
Hello, my name is Rahel Parikh, and today I'm going to be presenting my research on the design and evaluation of a scalable educational testbed for autonomous vehicle instruction. So today I'm going to talk about the motivation and the various objectives for this research, the theoretical analysis and preliminary design that we did for this, the prototyping and testing process, some of the major problems and solutions, results and analysis, and possibilities of future work on the same topic. So first, let's talk about the motivation and objectives. So in the world right now, There are a lot of different educational AV platforms. These small-scale autonomous vehicle platforms are widely used to teach various perception, planning, and control topics. And they're very useful because they enable real-world testing in safe classroom-friendly environments. Out of these various platforms, the most versatile and capable educational platform is the MIT RACECAR Neo. Now, what is the MIT RACECAR Neo? The MIT RACECAR Neo is a 1/14th scale RC car equipped with a vast and flexible sensor suite. It has an open source hardware and software, and it's used around the world in many different programs. And it's built off of a commercial RC car chassis from Tacon. However, several mechanical and electrical issues plague its use in education. But what's wrong with the MIT RACECAR Neo? Number one, vehicular variability. Identical cars built in the exact same way with the exact same parts can differ greatly in steering, speed, and backlash, making it very difficult to teach common concepts between different groups of teams and different cars. Additionally, mechanical fragility is a big issue. Low-quality manufacturer parts and designs can cause important parts of the car to often break, wasting instructor time and cost. And finally, supply chain obsolescence. As I said in the last slide, the MIT RACECAR Neo is built off of a 1/14th scale chassis that is bought from a manufacturer called Tacon. But this chassis has been discontinued, meaning that we can't make any more RACECAR Neos and we can't fix some that have been broken. So what's the solution? A new scalable testbed for AV instruction designed to address those specific issues. So here are the key objectives for this project. Number one, vehicular consistency. We want to keep the toe angle wobble, which is the wobble of the front wheels that steer the car, within 1 millimeter, and keep the velocity of the car plus or minus 1% error over a 60-second interval, ensuring its consistency in a straight line. Number two, classroom grade durability. We want the car to be as strong as possible, and we want it to be able to take as many crashes and hits as we know that will happen in a classroom. And to do that, we're going to re-engineer the entire mechanical and electrical architecture for durability and reliability. And three, supply chain independence. We want to make all major structural parts and subsystems fully custom made, reducing our dependency on any one specific manufacturer. Number one, theoretical design and preliminary analysis. First, when we wanted to design our car, we made a parametric dynamics calculator, which modeled combinations of different motors, gears, wheels, and other car parameters. And through these numbers, we came up with a final setup that gave our car a maximum speed of 11.8 meters per second, or approximately 26 miles an hour. And it had a maximum acceleration, theoretically, of 20.7 meters per second squared, which is equivalent to a 0 to 60 miles per hour of 1.3 seconds. And you can see here a photo of the calculator that we made, where you input all of the parameters on the left side, and you get all the results on the right side and the final performance metrics on the bottom. Now, we moved on to the 3D design and modeling process, where we designed the fully custom chassis in Fusion 360, professional CAD software. We redesigned the entire steering system using a dual bell crank linkage system with Ackermann geometry and a 2-bar spatial linkage powering the entire steering system for the maximum mechanical advantage. Additionally, the entire car was powered by a dual differential-driven 4-wheel drive drivetrain, and we upgraded the previous motor to a 12-volt brushless motor that spins at 11,000 RPM with 0.97 newton meters of torque. After this, we ran several simulations and finite element analysis on several high-load components, such as the shock towers, the suspension arms, and the new compliant shock-absorbing bumpers. And as you can see here, there's 2 photos, which are from a simulation of a 280 Newton frontal collision at 7 meters per second, basically just slamming into a wall. These simulations helped us make sure that our CAD model as a whole was fully very thought out, and made sure that we didn't have to continue the process of iterating without additional need for it. You can go next. Now, the prototyping and testing section. assembly and iteration. All of the different components of the car were made out of 3D printed PLA, TPU, and laser cut polycarbonate. There was we engaged in a circular process of testing, analysis, revision, and refabrication, where each part was heavily durability tested and optimized. As you can see here, on the left is a picture of the old race car Neo, and the right is a photo of the new one with a completely redesigned lower chassis. Now, for some of the major problems and solutions. The two major problems we had was gear skipping and damage due to some massive torque spikes. To solve this, we implemented a recursive motion profiler to apply time-based ramping and rate limiting to keep the gears from literally shredding apart whenever the motor wanted to spin faster. Additionally, the steering linkage initially had an insufficient mechanical advantage, meaning that the wheels did not have enough power to actually turn left or right. And to fix this, we redesigned the spatial two-bar linkage and improved the electrical architecture, providing the servo with 8.4 volts rather than 4.8 volts, giving it a lot more power. Now, onto our results and analysis. First, we decreased the wobble or play in the toe angle, which is the front wheels of the car, by 65%. Initially, it was 2.28 millimeters of toe wobble for the original race car Neo, and we lowered it to 0.82 millimeters. Additionally, the maximum deviation of the drivetrain velocity was 0.95%, which basically means that we ran the car at 10,000 RPM for 60 seconds, and the minimum and maximum RPMs were 9,920 RPM and 10,095 RPM, respectively, meaning that the speed was extremely consistent. And over nearly 32 components and the entire chassis base was replaced by custom parts, and only widely available commercial components were used, like screws and certain gears. Now, as for the impact that this actually had, the biggest change, or one of the biggest changes, was switching to this brushless motor. This significantly improved the motor speed control and efficiency, as shown with that 0.95% speed metric. Additionally, we learned that design coherence across mechanical, electrical, and software is extremely important to make sure the car works together as a whole rather than just different subsystems. And number 3, excess power is only useful if the rest of the system is designed to handle it. The motor that we chose for this research was far too powerful and required significant software limitation as to not destroy the car. And this drivetrain at 10% power significantly outpaces even the current race car Neo, underscoring how much excess power this thing has. And yeah. So now onto the future work of this. So in the future, what we want to do with this research is to re-specify the drivetrain. As I said in my last slide, we want to downsize the motor to match the drivetrain's durability. We want to also further durability test the whole chassis, do more collision testing, and do long-term tests on it. And we also want to build multiple units to quantify the inner vehicle variation. We also want to redesign the upper compute model and payload, because as it is right now, it has a very high center of gravity, and it communicates with the chassis using PWM, which is very susceptible to noise and doesn't have very much data transfer. We can't get information from the chassis using PWM as it is right now. So we want to lower the center of gravity and switch to CAN-based communication for two-way communication. Thank you. Any questions?
All right. Thank you once again to Raheel. Now for the questions. I'm going to ask 2 of these questions at the same time because they are saying the same thing. First of all, how much does this chassis cost compared to one you can buy off the shelf? And also, how expensive is your vehicle overall in comparison to the race car Neo?
Yeah, so in comparison to the race car Neo, it's approximately a similar price as the motor, the speed controller, battery. The battery is a similar price to the one we need for the race car Neo. And in general, it was designed as to not necessitate an extreme increase in price. But as we said, we do want to make some further changes to the motor and and some various aspects like the compute module. So it's hard to give a concrete number.
Okay, thank you. We're going to move on to the next question. How do you prevent the car from flipping during a turn if it has such an increased speed and acceleration?
So this research was mainly focused on the mechanical section, right? We're talking about the development of, the drivetrain and that. But yes, one of the things we do want to do is lower the center of gravity. What that will do is make it so that when you're going around a turn, you can hit it at a faster speed without flipping over. But also part of that is the students who will be using this car to presumably learn need to understand that if you're going extremely fast, you can't go at full speed. Even if you do that on a real car, you're going to end up flipping over.
All right. Next question. During the Grand Prix, why did your car that theoretically could go 0 to 60 in 1.3 seconds get caught up almost immediately by an older race car Neo?
So, as I said before, Chris, if you want to, actually, it's okay. But one of the things we did do is we severely limited this car's acceleration. This was because the car's acceleration made it extremely hard to control. It was pretty dangerous because just because we're also on the track with many other cars and we don't want to potentially hit other ones that are too slow and are in the way. And also in the Grand Prix, we got T-boned about half a second into the race. So that might have something to do with it.
All right, next question. Is your vehicle more robust than the race car Neo? Which means that does your vehicle have a higher chance of surviving upon crashing?
Yeah. So in certain cases, yes, and in certain cases, no. As this research was done on, it was a 4-week schedule. Some of the parts were 3D printed. Now, with the final version of this race car, if it was to be commercialized or used in place of the race car Neo, we would presumably replace some of these parts with custom metal components. However, the parts that have been finalized in their current state are extremely durable, such as the main base plate. The main base plate of the car went through significant abuse, and it's been it's extremely durable. And with the front and rear bumpers, it's been shown that they significantly help the car in terms of handling collisions.
Okay, thank you. Next question. How does your car compare in user friendliness to the race car Neo?
It's effectively the same. This was basically designed as a drop-in replacement for the lower chassis of the current race car Neo. And so all of the code is exactly the same from the user side of it. Some of the students while following code would maybe just require retuning some of the values or PID stuff to work on this car. But effectively, it's exactly the same in that sense.
Great. And final question. What is your ultimate goal with this project?
The ultimate goal here is to give us an alternative to what is the current MIT race car Neo. As I said, the drivetrain for it, the chassis for it, has been discontinued. It's the last of its kind, right? So this research is intended to give us a foundation for what will become the next version of this, so that this thing can live on beyond just being dependent on this single chassis from this one manufacturer.
All right, great. And that concludes our student presentations. So thank you to all 8 Beaverworks student teams and our research student Raheel for presenting. To the audience, I hope you learned something new today. And that will be all from us. So we'll see you back at the main stage. Enjoy the rest of this event.